Hey, welcome back to my Dbit grinder rebuild modification Renzettification video series. Well, this is the second video on this topic. Not going to call it a series yet, but here we are. Last time we did the bearing modification in here and some other little things. And today we continue with the swivel motion here because there is, in my mind, a significant problem with it. The 90-degree swivel motion is limited, means when you put this on top of each other and you move it like this, you can limit the motion to 90 degrees, from 0 to 90. You need that for grinding radii on the end of tools, for example. And this works by this pin here, which can be disengaged or engaged. It sits in the lower part here in this bore here, which is a bloody snug fit. This smaller diameter here pokes through this bore, and since it's eccentric, you can adjust the position of the 90-degree stop by rotating this. This works. The design intent behind it is good. Make it adjustable, so if it's not crazy precise, you can adjust it. And it kind of works, but it tends to not be very stable over time. For one, the pin in here has a little bit of slop, of course. Means your 90-degree position is not really crazy. When you move up against it, it's not very stiff or not very crisp. It's not a nice hard stop. And also, this limiting slot here is right in the cast iron, and gray cast iron is reasonably soft. And over time, this pin, the pin is smaller diameter than the slot here because it needs some room when you adjust it because it's eccentric. So the position of the pin in the slot can change. Means you have a line contact cylinder on concave radius, and over time this pin, which is slightly harder because it's steel, will work itself into the radius end here and move the end position, and you have to readjust it over time, and that's reasonably annoying. So I was thinking, yeah, I can do that. I was thinking I take a 6mm carbide end mill, cut off a piece, drill and ream into here, and drop in a piece of carbide, which is a very, very hard and stiff material. And this will give me a very good hard stop at the end of the slot already. That's the first point. And then we will see what we can do about this shot pin here that can be engaged and disengaged and is used as the stop. Either we will make the inner pin new from A2 tool steel, harden it and grind it and make it a very, very tight fit in this assembly here, or we come up with something entirely different. But probably I will go the easy route and just make the inside new. But for now we will do this. And let's find this. Okay, we have our center of rotation. And then we have this banana-shaped slot here. With this is basically a radius here. The slot is probably, yeah, this is 2.25mm radius. What we're going to do is we'll find the center of this radius here, rotate, move out a little bit, means by the radius, to here, drill and ream a diameter 6 hole. Then we will take a carbide pin, split it in half, and put it in there. So that means we already have. The other problem here is when the eccentric pin is adjusted, in the original design it will hit on different points of this radius, and this will make adjustment very, very sketchy, because at one moment and in one adjustment it might hit out here, in one adjustment it might hit here, or in front here, or here on the very far outside, and then you get in a weird pinching situation between the pin and the wall of the slot. So an eccentric pin in around the slot against the radius end is really not a very crazy nice design. So we're going to make a split in half carbide pin which forms a vertical wall at the end of the slot at the right position, and this is what we're going to do. Okay, for this work we need to mount this up on the rotary table because we need to do rotary alignment or precisioning. This piece already has a 6mm precision hole here in the center. So lining it up on the rotary table is easy because this has a Morse taper 2 in its center, and I have Morse taper 2 collet. So I put a carbide pin, i.e. a old end mill, in a collet, and just drop it in the center bore of the rotary table. So that's your cheap alignment trick of the week. And then we can just push this, put this over here, and this is very good aligned now. Yeah, to get it out you need to either pull it out with a plier here on the pin, or you need to knock it out from the back with the copper drift. Okay, then we have T-nut here, 6mm stud. Part goes over the stud and over the pin. So drops over the pin. This is a machined surface, precision surface, reasonable precision. So we don't have to worry about it. Drop it on here. Washer, nut. And there's your setup. Tighten it down with some reasonable torque. We're just drilling out here. I might put a screw jack under here, but in all honesty, probably not necessary. So this looks very promising. Let's get let's get a tool in here and do some measuring. Probably dial test indicator. I have a dial test indicator here. I just rotated the rotary table to 0 degrees down here, and now I pick up the end of the slot, the end of the radius here, by centering on the radius here. And zero out my DRO. Centering on the end of an arced slot in the radius is a little bit tricky. But with that test indicator it kind of works. I moved the table around in XY until I got kind of a 0 reading all the way around in what I have access to. So it means I start here at 0, spin it around at what's almost 90 degrees. I also have 0, and when I get over here I have also 0, and then it drops off. This is when we arc back into the slot, into the open void. So this is basically 0. little bit tricky, but this is where a dial test indicator for the milling machine is really valuable. You can't do this with an edge finder, and even with a Heimer 3D probe, kind of tricky to do. What would make it easier is if we had a pin that we could stand in here, push it all the way up to the end of the radius, maybe super glue it in and then indicate on that pin. Oh, you know what would work? That just came to my mind. We can just use a ball bearing ball, and this will track nicely in this arced slot and will end on the radius here. If you roll it all the way to the end of the slot, it will precisely sit on the end of the slot. Move it there, add a drop of super glue, then indicate on the ball. And that would work exceptionally well, I'm sure. But in this case, I already got my position. This is precise enough because the pin that will ride in there has adjustment built into it. Okay, what I just did was brain fart. We centered on this diameter here, means center position here, but I'm not interested in that position. We want, if this is the center line of the slot, which is a circle, we want this position here at the end of the slot so we can put our hole for the carbide pin, for the split carbide pin in here. So this is off. One way to do it, we could take the radius of the center line of the slot and calculate how much angular movement we have to do to move from here to here. That would be the proper way to do it. Or we put a pointy thing in the spindle of the mill, a pointer, a center, and we visually align the pointer with this edge by rotating the rotary table. We are already on center, on our radius position of the slot, so we just need to rotate it in until we're at this point here. And then to do the other side, we just spin the rotary table by 90 degrees. What's important is the relationship between the ends of the slot, not the absolute position, because the absolute position can be adjusted by spinning the eccentric pin. And that's exactly what I'm doing here. I spun the rotary table around until the end of the slot was in line with the center that I have in the spindle of my mill. So that's my 0 position now, and that's where I'm going to drill and ream or machine a hole with 6mm diameter for the split carbide pin. I drilled the first one. Now we rotate the rotary table by 90 degrees plus 6.2 degrees, because that's the angular motion that I figured out in CAD to get my right positions. And since I didn't touch my XY, these are now on a perfect arc. We might have to shave off some material here later because there is a little bit left where the old radius ran out into the arc. But that's not really an issue. Now I need to make 2 carbide pins. Means I have to cut some end mills off, some old end mills. Split them on the surface grinder in half, relatively precisely in half. And then we will glue them in here and align them correctly. You have the 2 6mm circles here. These are the ends of the arced slot, and 2 5mm circles concentric to it. These are the diameter of the shot pin that's limiting the swivel motion of this whole thing. Then I put them at a 90-degree relationship to each other, and I drew 2 tangents to the 5mm pin out here. These 2 lines are tangent to the shot pin here. And then I just measured the angle between the 90-degree relationship and this tangent here, and this is 6.2 millimeters up here. Here, 6.2, and down here, not. Well, it's also 6.2. These are the 6-degree and 12 arc minutes that I set the rotary table off the 90 degrees that I used before. Solving a geometric problem like this in CAD is way safer and less prone to error than sketching it out and doing trigonometry on a piece of paper. At least for me. I tend to make stupid mistakes when I do math. Well, I do mistakes in CAD too. Take that with a grain of salt. Over at the tool and cutter grinder, I have an old 6mm carbide end mill in here. I'm using the end because it's already chamfered, and the hole I plunged into the swivel mount was done with an end mill, and the end mill has a little bit of corner chamfer, and with this chamfer here on this part, on this carbide plug, we won't get any issues where the part doesn't seat all the way down into the bore. So now I'm using my small caliper to set the width of my part here. There we go. And then we just saw it off. And yes, this diamond cutoff wheel is missing a little chunk, but it's still cutting very nicely. Two pieces of carbide, 6mm diameter, about 10mm length. We will cut them to final length on the surface grinder and split them in half. As you can see, I split the first pin in half. This is now our new end stop with a nice flat surface and also a very non-Brinellable material. I used the other pin on the other side of the vise to balance out the clamping forces so the moving jaw doesn't rack like crazy. So we put the next piece in. Lock it in place. We touch off on the end with the side of the grinding wheel. Move over 4mm, plunge down 3, and then traverse out. I'm traversing out because, and also I'm grinding on this side of the pin, because I know that my diamond grinding wheel is worn more on the right side than on the left side, and by that way I still get a flat surface. When I use the leading edge, the more unworn edge as a trailing edge when traversing over the surface. Hard to explain in words. Okay, we're very close up, and this is going to be very loud because I'm running dust extraction, because carbide causes all sorts of problems in your lungs. Okay. Yeah, 3.002 millimeters for a mechanical stop. That's very good, especially since my coordinates are done on a milling machine and there is an inherent less accurate process than on this machine because the machine itself is less accurate. Here are the 2 pins before we permanently glue them into the swivel mount. I'm already putting on some gloves because next step will be to Loctite those carbide pins in place. The gloves are for the Loctite because since the last video I got a new bottle of Loctite 648 bearing retaining glue or bushing retaining glue or whatever it's called, because running out of Loctite is very annoying. So we need to angularly align these pins, and the center line of these pins, the flat, needs to run through the center of this bore of the axis of rotation. And the idea I had, I take a Dbit, which is split in half, put it in here, and I take a straight edge or a scale, depending on who you ask. I put the pin in almost all the way, line up the scale to the pin, and as you can see, when I rotate the scale, the pin will rotate with it. Then I can just align it with the Dbit in the center here, get the scale out of the way, and have the pin drop in all the way into the glue. So this should work. So let's get this. Okay. This is acetone. Just for a light pre-glue cleaning. By the way, acetone will eat through pretty much every glove out there. Don't touch it too long with the gloves. It will permeate through pretty much any glove, except for extremely heavy industrial rubber gloves. But you cannot work to a fine grade or fine detail. Also, I ran the 6mm end mill that I used to plunge these holes. I ran it through the arced slot to clean up the remaining material. And now we're good to go. And if I had thought through it before, I would have left these a millimeter longer so they stick out and would make alignment easier. And then I would grind them flush. But these are already the right length. In fact, they are 0.1 millimeter shorter than the height or the depth of the hole here. But it's always easier in hindsight. By the way, that's also in case with the commenters. Of course, when you comment on a video how I could have done something better, and often that's very true, often I choose a solution and I go with it. But that's when I'm in the shop and working and want to get it done. When you watch this video and comment, you have all the time in the world to think about it and go through options that I might not have thought about. And I read all those comments and I really appreciate them. But it's not like a you should have done, it's more like another option would have been too. And often I have even thought about the other option, but for one reason or another, for example, that my skill level is for one solution not high enough, or my equipment is not suitable for the solution that has been given. Okay, this is looking very, very good. I'm just double checking with the scale here. Yeah, this is looking very good. So while I appreciate I absolutely appreciate every comment. I pretty much read them all, as long as you don't as long as you're not shitty to me, like, you're dumb, you should have done, or you're young, you have no clue what you're doing, or yeah, if you would do this in my shop, I would fire you. As long as you don't do that, I appreciate every comment. You don't have to agree with what I do. I don't have to agree with your recommendation, but you know, I will read them and I will usually think about it, and maybe not always comment on it, but you are heard. People, you are heard. So I appreciate the very very nice comment culture under my videos a lot. So we glued those pins in and they are aligned properly, and now we wait for the Loctite to set. So I put it all roughly together with the old index pin in here, and I moved the swivel arm up here to the end stop position and zeroed out the style. And I just want to see if I had a brain fart somewhere hidden in there, and if I get my 90 degree, and the answer is yes, I get my 90 degrees perfectly. One thing that I had forgotten is to put a counterbore in here for the screw that holds the shaft, the swivel shaft in place. So let's do this. We're over at the drill press because the milling machine is set up for a production job. So I have an aluminum plate here because the drill press table has this huge hole in the center, and the aluminum plate spans over it. The casting sits just with this machine surface here on the aluminum plate. I have a screw jack back here supporting the casting, and I'm using this Copal spanner on top of the dovetail here, and by having the screw jack back here, the part is held securely and level in place. And for alignment, I have a 6mm pin in the drill chuck, and I can just pick up the precision bore here in the center. Get my screw jack in and clamp down on it. I don't have a piloted counterbore for this hole diameter and counterbore diameter combination, so I'm using a 10mm drill and then a 10mm flat bottom drill to create the flat surface for the screw. So first of all, using this one. So zeroing out my DRO. Okay. That's most of it. And now we change to this one to remove the taper. Finding my height using a 6mm pin. And there we go. Yeah, and now how to get the screw back out. So this wants to chatter a little bit, so I'm turning down the speed. There we go. And of course, we chamfer the inside of the counterbore where it goes into the smaller hole. There we go. And the large countersink to remove the top edge. And there we go. You might remember this little issue we created last time, where by boring out the center of the swivel mount here, we broke into the bore, and I sawed a piece of gray cast iron to size, and now I'm shaping it using the belt sander to be a nice fit in there. And I'm going to surface grind it to be parallel, and then we're going to glue it in with Loctite structural adhesive, an acrylic glue. I think this is a good enough fit up. Just going to surface grind it. Okay, just only surface grind the filler piece that we made to thickness. Well, didn't grind it to a specific dimension, I just cleaned it up. Now we'll glue it in, and later we will drill through from the back. Let's quickly talk about the clamping of this rotational axis here. That was a question that came up on the last video. So the original design was, there was a screw coming in from the side. It had like a 90-degree tip on it, and there was a groove cut into the shaft with a conical surface on it, and the screw pressed with its angled tip against this angled surface. And I'm not entirely sure what the design intent behind that was, but my guess is they wanted to pull the shaft down onto the mating surface up here when you tighten the screw, so it takes out any slack. That works. That's a good idea, but the problem is when you run the screw with its 45-degree angle against this 45-degree cutout in the shaft, this is like a bevel gear based on friction. And when you tighten it, it will always try to spin the swivel arm a little bit. So this is, well, nice try. What I came up with, I'm basically doing the same. I'm pressing against the shaft because any other locking method would require massive changes to the casting, and I don't want to make a science project out of this thing. So what I'm going to do is I take a piece of a 6.8 millimeter high-speed steel punch, cut it off. This fits in here. This is the hole for the locking screw. I will cut off a piece. So if we take a top view like this, it will be like this. Pressing up against the shaft, and I will have the kip handle. I will cut it off, drill out the end, press in a ball bearing, and then I have a hard ball against hard surface situation, and the hard V against the hardened shaft with a two-line contact. So this is a very good clamping situation. Yes, a shaft is not supported on the back here, but I'm extremely close with this clamping screw to the needle bearing. So the unsupported length is about 5 millimeters. So I'm not worried or massively worried about bending the shaft when I tighten down this clamping screw. Off camera I made this little pusher piece, cut off a piece of the high-speed steel punch, put it in this V-block, tilted the grinding wheel by 15 degrees, ground one side, flipped the V-block around up against the fence again, ground to the same depth, and now I have a nicely centered V cutout in this punch. A very similar geometry that you would use on a paper punch, because it folds the waste over before it pushes it through and prevents the waste from sticking in the punch plate or in the die. That's the correct word. And just for reference, this is the grinder with the wheel head tilted by 15 degrees. To go back, I will just loosen the screw. Well, we can do that now. Let's go back to 0. You loosen the central screw, and then you have this pivot here. You push in your conical or your taper pins. Give them a light tap. Those loose nuts, you just finger tighten them against the castings so they don't fall out or fall off. And you tighten the central bolt that holds the wheel head in place. And I find this alignment here to be suitable for pretty much everything, because you're dressing the wheel square to the movement of the grinder anyway. And this is the pusher piece, and this gives a nice 2-point or 2-line contact with our hardened swivel shaft here. And since this both is a very hard surface and we're making line contact, not point contact, I'm not worried about wearing into the shaft or into this pusher. We need to shorten this kip handle here, and if you didn't know, you can take these apart. You take either a Torx or your least fitting flat-bladed screwdriver, and you undo the screw here. Out comes the screw itself, a spring, the handle, and then you have this piece here, which is basically the spline and the bolt itself. And the spline intersects with this die-cast spline contour in the handle, and that's what allows you to adjust the position of the handle. Very nice pieces. I really like these. So we need to cut this down and put a ball bearing into its end. I drilled out the end of the screw, 4.5 millimeters, pressed in a 5 millimeter ball bearing, hardened ball, and now we have a contact, a very small contact patch, which is also not influencing each other, between the hardened ball and this hardened surface of this pin. And I expect that this will give a very, very crisp clamping action. So we put this pin in. See for the correct orientation of the V cutout. Drop the shaft in. Put our clamping handle back together. Spring, screw, worst fitting screwdriver. Okay, it's working, and let's see if we can get this to start in the thread. Yeah. So yes, that's a very nice clamping action. Rotating. Wait, let's put it together. So we get a feeling for how it behaves. Screw. Bolts it together. Now we have our swivel motion, and now when we this is a very nice clamping action. Yeah. This feels about the same as on a real Deckel SOE tool and cutter grinder. But somehow I miscalculated the length of the screw by about a lot. And I'm not sure what happened here, so I have to remove another 10 millimeters and press in another ball bearing because I'm stupid. That happens all the time. So I'm going to remove another 10 millimeters, press in a new ball bearing, and try again. I shortened the screw, and I'm about to press in a new ball bearing. I have a piece of some precision ground flat stock here, just so I don't brunel my nice Weiss jaws with the hardened bearing ball in here. And there we go. I drilled. Overall depth of the hole is a little bit less than the diameter of the ball, so the ball sticks out the front. There we go. Let's try again. Okay, let's put this handle together again. Put it in here. Now it should be. Oh, no. Oh, that's nice. Now I have just a little bit of overhang here. Got my locking action. So all of this really feels nice. I really like this. And also, when I tighten this screw, this does not influence my rotation at all. I'm at the drill press and I have the whole casting, the base casting of the Dbit grinder on the drill press, and I'm drilling. I made this plate. This is the extension where the moment arm gets a rest on, and this is bolted with 3 screws to the casting and has 3 leveling screws to get it perpendicular and parallel to both the main axis of travel and the grinding spindle. Probably more important to get it level to the main axis here. I aligned the side of this plate with a steel scale to the main axis, put the main axis in, and then just used steel rule against the plate here and get it in a line, because the rotational alignment here is not critical at all. It just needs to be kind of straight. Strap clamped it down in that position. Now I'm using a drill to pick up the hole locations of the 3 M6 screws that bolt this plate to this casting, and drilling through with a 5mm drill and run an M5 tabs through there, all on the drill press without disturbing the setup. And what allows me to do this on this machine without having to loosen the clamps is the fact that the table rotates And also the table swivels on the column. This allows me to use this machine like a poor man's radial arm drill, just inverted. That way I can reach pretty much all positions that I need in one setup. Very old school way of doing things here. Now we kind of align it. And then we play around with our two rotations. It's two overlaid rotations to get any XY position here. That works. It's relatively slow, but this allows me to do this on the drill press, which has a huge work envelope compared to my milling machine. I could put an indicator in the spindle and sweep the hole, of course, but we're just transferring bolt hole positions. So looking at the drill bit from two directions and checking how it deflects is more than adequate in this case. So it should be good. Locking the two axes, double checking, feels good. I drilled a little dimple with the 6.3mm drill, which is the through hole in this plate. And now I change to a 5mm drill. There we go. And here's the tap. And we will just power tap this. Okay. And I'm putting in screws to make sure that the setup does not shift at all once I drill the last hole. With those two screws, the setup gets way more safe. With the first hole not drilled and no screw in it, it was a little bit touchy, but once I had the first screw in and the two strap clamps here, all was good. So moving to the last position here, 6mm drill, or 6.3 in this case, as our pilot, or and that's why I bought a large drill press. There we go. Lock it, double check. There we go, and tap. Jump forward in time, it's pretty much 1 year later since I last filmed on this project. And this is the current state of it. It changed color from gray, if I remember correctly, to 6011 Reseda Grün. Most beautiful color out there. And this is how the moment arm for the main axis will look like. This is just bands out from a piece of flat ground stock so far. This will sit permanently on the main axis, and this gives a very positive depth stop for this rotation motion, because this lever is so long compared to the very short lever on the original swivel stop. And this plate back here is because this main axis can of course move in and out this way. This is not the final length of the plate. I will bandsaw and mill it off to the final length once I decided about the overall setup. Also, I ordered some parts, all the seals for the main shaft, also seals to go inside here. I hope to get back to this in a reasonable time frame. I really hate not having a working Dbit grinder in the shop. I have the tool and cutter grinder and I have a surface grinder, but Dbit grinder is hard to beat for very fast and quick and dirty setups and just to grind something. And also it's doubling as a bench grinder in my shop, which this shop doesn't have a dedicated bench grinder. So that's some motivation there. So thank you all for watching, and I'll be back.